On the weekend of May 20 to 22, 2016, an extraordinary engineering feat took place on the A12 highway in the Netherlands, where a 70-meter-long tunnel was successfully installed beneath the busy motorway in just one weekend. This remarkable project demonstrated the precision, innovation, and coordination that modern civil engineering can achieve when faced with tight deadlines and complex logistics. The project took place near the town of Ede, located in the Gelderland province, where the Dutch National Highway A12 connects important cities like The Hague and Arnhem. The tunnel was part of a broader infrastructure project to improve traffic flow and accessibility in the region, specifically to connect the N224 road with the Ede-Wageningen railway station. Instead of closing the road for weeks or months, the construction team opted for an accelerated method, installing the tunnel in a single weekend to minimize disruption to the tens of thousands of vehicles that travel the A12 daily. Preparation for the tunnel installation began months in advance, with the tunnel being pre-constructed beside the highway. The innovative construction approach, known as the cut-and-cover method, allowed the tunnel to be built to precise specifications before it was moved into place. On the weekend of May 20th, workers closed a section of the A12 and immediately began removing large portions of the motorway surface. Massive amounts of sand and earth were excavated, clearing the way for the tunnel. Using advanced hydraulic jacks and powerful machinery, the tunnel, already weighing thousands of tons, was slid into position beneath the highway. The speed and accuracy with which the tunnel was moved were crucial to ensure that the installation went smoothly. The entire process was captured in an awe-inspiring time-lapse video, which showcased the precision of the operation. Within a short span of 48 hours, the tunnel was in place, the highway was repaved, and traffic was allowed to resume, almost as if nothing had happened. This seamless integration of a major infrastructure component over such a brief period was a testament to planning, teamwork, and the use of cutting-edge technology. This project not only highlighted the capabilities of Dutch civil engineering, but also set a new standard for minimizing disruptions during major infrastructure works. The A12 tunnel installation was lauded as a success and an example of how infrastructure projects can be executed efficiently while balancing the needs of modern transportation networks. In April 2024, the historic River Deel Bridge, located in Askeaton, County Limerick, Ireland, is set to be reinstalled after extensive restoration work. The bridge, which dates back to the 19th century, has been a vital crossing point over the River Deel, linking the town and providing a crucial transportation route for residents and travelers alike. The reinstallation follows a significant restoration project initiated after structural concerns arose, leading to its temporary closure. During the process, engineers carefully dismantled the bridge, preserving its original stonework and iron railings, while modernizing its internal framework to meet current safety standards. The reinstallation marks a major milestone in the town's ongoing efforts to preserve its architectural heritage while ensuring the safety and functionality of its infrastructure. Local authorities and preservationists worked closely to maintain the bridge's historical integrity, as it stands as a symbol of Askeaton's rich history. In April 2024, a significant engineering project took place on the historic Killaloe Bridge, a vital crossing linking Killaloe in County Clare to Ballina in County Tipperary, Ireland. The project, known as the Killaloe Bridge Lift, involved a temporary raising of the 300-year-old structure, which dates back to the early 18th century, to accommodate modern infrastructural needs. The purpose of the lift was to enable the construction of a new pedestrian bridge and the continuation of the Killaloe bypass. This bypass is a critical part of a larger transport infrastructure plan aimed at reducing traffic congestion in the picturesque twin towns. The existing bridge, known for its narrow and antiquated design, had long been a bottleneck for both local and through traffic. The lift operation was a carefully planned process, involving the use of hydraulic jacks and heavy machinery to elevate the bridge in sections. Engineers took great care to ensure that the structure's historical integrity was maintained, as Killaloe Bridge is a protected heritage site. The temporary raising of the bridge allowed for the placement of essential infrastructure beneath it, ensuring minimal disruption to water traffic along the River Shannon. The Sombrio Bridge on Highway 14 near Port Renfrew underwent a major upgrade, transforming from a narrow, single-lane timber bridge into a modern two-lane structure. This new bridge spans 124 meters and is built with concrete and steel, representing a significant improvement in both capacity and durability. The project also involved realigning a 1.2-kilometer section of the highway to better match current safety and travel standards. The newly aligned section of the highway was constructed with 3.6-meter wide lanes and 1.5 meters paved shoulders, accommodating both vehicles and cyclists, while providing safer conditions for all road users. The new alignment has been designed for travel at 70 kilometers per hour, enhancing the flow of traffic and overall accessibility along the route. In addition to upgrading the bridge itself, the project also involved the paving and realignment of the bridge approaches, ensuring smoother transitions for vehicles entering and exiting the bridge. This realignment extends eastward, with 5.4 kilometers of Highway 14 resurfaced, ending near Lyons Creek. This comprehensive resurfacing improved the overall quality and safety of the highway, benefiting both local commuters and visitors traveling to the scenic areas of Vancouver Island's west coast. Further safety enhancements were made to surrounding bridges as well. The approaches to the Baird and Merton bridges were widened to improve traffic flow and accommodate larger vehicles. New roadside safety barriers were installed at these locations to increase protection for motorists, especially in hazardous weather conditions or at night. Additionally, the Sombrio No. 3 bridge received significant upgrades to its concrete structure, further reinforcing the integrity of the highway network in the area. The intersection of North Terrace and King William Road in Adelaide is a key focal point for both pedestrians and vehicles, serving as one of the city's busiest and most historically significant junctions. In 2024, a significant upgrade project was launched at this intersection as part of Adelaide's broader efforts to improve traffic flow, pedestrian safety, and accessibility. The intersection, located at the heart of the city, connects major institutions such as the Art Gallery of South Australia, the University of Adelaide, and Parliament House, and it experiences heavy traffic due to its proximity to key tram and bus routes. The ongoing works are designed to address congestion issues while modernizing the area to support future urban mobility. One of the primary goals of the project is to improve pedestrian safety and accessibility. Given the high volume of foot traffic, particularly from students and tourists, enhancements include wider pedestrian crossings, improved signal phasing, and dedicated pedestrian traffic light systems. These changes will ensure a safer and more comfortable walking experience. Another significant focus is on public transport integration. The North Terrace and King William Road intersection is a hub for tram services that connect to Adelaide's north-south corridor. The upgrade involves track realignment and new tram infrastructure to improve the efficiency of public transport and reduce delays. Traffic signal upgrades and lane realignments are also being implemented to enhance vehicle flow, minimizing wait times for drivers at peak hours. By introducing smart traffic management systems, the intersection will better accommodate the mixed demands of public transport, cyclists, and private vehicles. The Cardiff Road Bridge replacement in Newport is a significant infrastructure project that forms part of Network Rail's ambitious £40 billion railway upgrade plan, which aims to electrify the South Wales Main Line. This electrification project is set to bring a faster, greener, and more reliable railway service. improving connections between South Wales and major cities like London, benefiting both passengers and businesses. During the replacement of Cardiff Road Bridge, a single-lane traffic management system was implemented to manage traffic while maintaining access to the road. This temporary arrangement was necessary while the old bridge was dismantled and replaced with a new, stronger structure. The successful completion of this project reflects the commitment of Network Rail and its engineers to deliver the work on time while minimizing disruption to local residents and road users. Andrew Griffiths, the program manager for Network Rail Wales, extended his gratitude to the local community for their patience during the bridge replacement. He emphasized that the upgrade is a crucial part of preparing the railway network for electrification. The new bridge is a key component of this broader effort to modernize the railway infrastructure, which will bring multiple benefits such as quieter trains, reduced environmental impact, and more reliable services for passengers. Additionally, the electrification of the South Wales Main Line will improve travel links between South Wales and major urban hubs, enhancing connectivity for commuters and businesses. Following the completion of the main bridge replacement, Network Rail engineers are scheduled to return to Cardiff Road in June to raise the bridge parapets as part of ongoing safety enhancements. Although this work will cause some temporary disruptions, with the bus lane being closed, the road itself will remain open for general traffic, minimizing the inconvenience to motorists. This bridge replacement is just one aspect of the wider railway improvements taking place in Newport. Parallel to the Cardiff Road Bridge works, Network Rail is also undertaking significant upgrades to the Bridge Street Road Bridge in Newport's city centre. This project requires the complete closure of the bridge to all traffic from May 2016 until late 2016. Such upgrades are essential to accommodate the future electrified railway and to ensure that the infrastructure is capable of supporting the demands of a modern, high-capacity rail service. The Whelan Bridge replacement was a significant infrastructure project carried out as part of the larger Lewis cross-city expansion. Located on Fassaw Road in Cabra, Dublin, the bridge, named after footballer Liam Whelan, who tragically died in the 1958 Munich air disaster, was a crucial part of the Lewis light rail system's extension to connect the Green Line to Broombridge. The project, involving the replacement of the existing bridge, ensured the integration of new tram lines while also improving road infrastructure for the area. Purpose of the replacement: the existing Whelan Bridge was no longer sufficient to meet the demands of the new Lewis Cross City route. The structure, built in the mid-20th century, had limitations in terms of capacity and load-bearing ability, and it needed upgrading to accommodate the modern tram system alongside vehicular traffic and pedestrians. The extension of the Lewis line necessitated infrastructure that could handle the extra load and provide the clearances required for both the trams and the underlying rail lines. The replacement of Whelan Bridge followed a carefully planned and phased construction process to minimize disruption to the surrounding community and existing transport networks. A key feature of the construction process was building a new bridge deck adjacent to the old one. The new deck was constructed on a temporary supporting structure, which allowed work to proceed without causing significant disruptions to traffic flow on Fassaw Road. This method of constructing the deck separately before installation helped speed up the overall process and reduce the need for extended road closures. Once the new deck was completed, the old bridge deck was removed. This step was carefully coordinated, as it involved dismantling the existing structure without damaging the surrounding infrastructure or interrupting the underlying rail lines. Specialized cranes and equipment were used to remove the deck efficiently and safely. With the old deck removed, the next step was installing new foundations and abutments, which would support the new bridge. This phase of the project was crucial, as the new foundations had to be robust enough to support both the increased vehicular vehicular load and the Lewis trams. The foundations were designed with long-term durability in mind, ensuring the bridge could meet modern safety standards. After the new foundations and abutments were in place, the new bridge deck was moved into position. This process required precise engineering, as the deck had to be aligned perfectly with the surrounding road and rail infrastructure. The use of advanced construction techniques allowed for the smooth transition of the new deck into place with minimal disruption to ongoing transport services. The replacement of the Whelan Bridge was a crucial component of the Lewis Cross City project, which aimed to enhance Dublin's public transport network by extending the tram line from the city centre to the northwestern suburbs. The project improved transport connectivity in Cabra and the surrounding areas, reducing congestion and providing residents with better access to public transport. Additionally, the new bridge provided an upgraded, safer route for both vehicular and pedestrian traffic. The Parson Street Underbridge, located in the southern suburbs of Bristol, is a crucial part of the city's railway infrastructure. It serves as an underpass for the A38 road beneath the Bristol to Exeter railway line, managed by Network Rail. This bridge is not just a simple structure, but a reflection of the intricate engineering solutions employed in the Victorian era when the British railway system was expanding rapidly. Over time, it has been subjected to various upgrades and repairs, ensuring its functionality and relevance in modern times. The Parson Street Underbridge dates back to the mid-19th century, a period marked by rapid growth of the railway network in Britain. The railway line it supports, the Bristol to Exeter line, was opened in 1841 and was one of the key routes designed by the famous engineer Assembled Kingdom Brunel. Brunel's work on this line was particularly significant because it provided an important link between London and the southwest of England, facilitating not only passenger travel, but also the movement of goods. The underbridge became necessary due to the road and rail infrastructure intersecting in this area. To avoid disrupting the traffic on the vital A38 road, an underpass was constructed. This road is a key route connecting Bristol to other cities and regions, including Exeter and Taunton. The underbridge allowed both rail and road transport to coexist without impeding one another's flow, a necessity for the growing industrial traffic in the 19th century. Although the Parson Street Underbridge is not as widely celebrated as some of Brunel's more monumental works, its design is nonetheless a testament to the ingenuity of Victorian engineers. It consists of multiple spans that carry the rail tracks over the road below. Initially built using traditional materials like wrought iron and brick, the bridge's design reflects the architectural preferences and technological limitations of its time. The underbridge was constructed with robustness in mind, using a girder design to ensure it could withstand the weight of the increasingly heavy trains that would pass over it. The structural integrity of such bridges was paramount in an era where railways were becoming the backbone of Britain's industrial and commercial economy. Additionally, the bridge had to be carefully aligned with both the railway and road, considering the steep gradients in the area and the curvature of the tracks. Over the years, the Parson Street Underbridge has undergone several renovations and reinforcements. As the volume of traffic on both the road and railway increased, the bridge needed regular maintenance to ensure safety and efficiency. In the 20th century, as rail and vehicle weights grew heavier and traffic density increased, the structure required upgrades to meet modern standards. One significant intervention occurred in the 1960s when major structural reinforcements were made. The bridge's foundations were strengthened, and the girders were replaced or reinforced to handle the increased load of modern trains, which were significantly heavier than their Victorian predecessors. Additionally, improvements were made to ensure the road below could accommodate growing automobile traffic, particularly given the A38's importance as a regional artery. More recently, the underbridge has been subject to inspections and repairs as part of Network Rail's ongoing maintenance program. Modern materials like reinforced steel and concrete have been introduced in certain areas to bolster the original Victorian construction. The goal of these updates is to ensure the bridge remains functional for decades to come, despite the ever-increasing demands placed on it by both road and rail traffic. Today, the Parsons Street Underbridge continues to play a vital role in Bristol's transport network. The Bristol to Exeter railway line remains a crucial route for commuters and freight trains, and the A38 road is still a key conduit for traffic heading in and out of the city. The underbridge ensures that both can operate seamlessly without interruption. The bridge also serves as a reminder of Bristol's rich railway heritage.